Today, we're starting with chapter 3 on analog computing. So let me start by showing you the overview of chapter 3 on analog computing. So in this chapter, we will first recall some mathematical background, simple calculus like derivative and integral of functions. Then we will recall equations and systems of equations, and in particular, I'm going to give you a very short introduction to differential equations. Maybe you have not learned about differential equations yet, but the background of the differential equations needed for this chapter will be provided in this chapter. So as long as you know about integration and differentiation, then you're going to be good. Then I'm going to recall the engineering, the mechanical differential analyzer invented and built by Vannevar Bush, and then proceed to Claude Shannon's mathematical theory of this differential analyzer. Namely, Claude Shannon characterized which continuous functions can be computed by the differential analyzer and which ones cannot be, based on certain types of differential equations that can be expressed in the differential analyzer, while others cannot be expressed. And this is kind of a computability theory for analog functions. And unfortunately, it's difficult to create a complexity theory of analog computation. So, in discrete complexity, we know about polynomial time computable problems, P versus NP. And similar in the analog setting, efficiently computable analog functions versus inefficiently but computable analog function. That's actually very challenging, and that problem, actually the definition has only been devised in the last few years. And maybe we will have time to talk a little bit about complexity, but maybe we also just end this chapter by pointing out how the Zeno effect prevents a naive complexity theory. So that's our purpose. That will probably keep us busy for the next few sessions. But remember that tomorrow we want to review your progress of your own presentations. I'll say more about that at the end of today's lecture, so stay tuned for that. Okay, now let's dive into recap of calculus, derivative, and integration. And to this end, remember how we already discussed the difference between discrete and continuous functions. And mathematically, the discrete functions can be described, for example, as functions from natural numbers to natural numbers. So when the function has value 7, or it can have value 8 at some point, but it cannot have value 7.5 between 7 and 8. And that's what it means to be discrete. And that's what allows to recover discrete function even in a noisy environment. When a value is close to 7, then probably the value is equal to 7 because there's no intermediate value. These are functions from natural numbers, functions on vectors of natural numbers, like d-dimensional vectors are formalized mathematically in this way, with this d here, d tuples of natural numbers. Interestingly, there's not much of a difference in the discrete case between functions of one natural number or functions of several natural numbers, functions of vectors, because there's this so-called pairing function that allows to combine several natural numbers into one natural numbers. back and forth, so we can encode two natural numbers into one natural number, and we can then recover from this code the original two natural numbers, and this is called a pairing function. You may have heard of it. It's also known under the moniker Hilbert Hotel, because in Hilbert Hotel, even when all hotels, Hilbert Hotel has infinitely many rooms, but even when all rooms are occupied, and then a bus comes in with infinitely many passengers, then by rearranging the rooms in Hilbert's Hotel, one can make room for infinitely many more occupants. And this is described mathematically as this pairing function, which takes two natural numbers. Imagine the first number is the room number of a previous occupant, and the second natural number, imagine that this is the seat number of the passenger in the infinitely large bus arriving. And this the value of that pairing function is the new room number after the passenger has been moved. And so this is the mathematical expression. And it's a nice exercise to show that this function is actually bijective. So meaning it is injective. No two people will be assigned the same room, and it is injective, so that from the room number after moving, one can recover who and where the occupant in the new room came from, which seat in the bus it had, and which previous room number he or she had. So this is a recap on discrete mathematics, as you have learned probably in CS 204 at KAIST. But the essence is in the discrete setting, it doesn't make much difference if we have functions of one natural number or several natural numbers, because one can encode these several natural numbers into one natural number back and forth. And probably intuitively have known that, because in computer science we usually talk about binary encoding, encoding natural numbers as finite binary string. This is a terminology for finite binary string, argument and value. And of course, one can combine two finite binary strings with some delimiter into a longer finite binary string. So here it's maybe more intuitive that there's not much a difference if we have just one finite binary string, or if we have D finite binary string, each one encoding a natural number. And all this is very different when we now move to the continuous setting for analog computing. In analog computing, we're interested in functions from real numbers to real numbers, not natural numbers to natural numbers. And here we have a function, we also have vector functions which take vectors, d-tuples of real numbers. And we also may have functions that are only defined on an interval, not in all real numbers, such as the unit interval, or d-dimensional vectors on the with values from the unit interval. And all these now suddenly make a difference. This is a basic topology, and we will be interested in recalling whether such a function is smooth and in what sense, right? So for example, function can be continuous, like this one, can even be differentiable, so there are no corners, or it can have corners, and all this suddenly becomes important. There are functions which are not differentiable, and this is very different from the discrete setting. Also, in the continuous setting, we cannot simply combine several real numbers into one real number. I mean, yes, we can do that. We can, for example, add two real numbers to obtain one new real number, but then it's not possible to recover from that sum of two real numbers. The original two real numbers cannot be recovered, because if you add, for example, 1 and 3, the result is 4. And if you add 2 and 2, the result is also 4. So if I tell you the result of the coding is 4, you have no means of recovering whether the original two numbers was 1 and 3 or 2 and 2. And there's a famous theorem, very deep theorem by Luitzen Egbertus Jan Brouwer, famous mathematician, constructive mathematician from the Netherlands, who actually proved that this is fundamentally impossible to encode several real numbers into one real number back and forth in a continuous way. It is possible in a discontinuous way, but here we're only interested in continuous function. It's a very deep theorem, so I just want to report it here. And if you're interested in mathematics, this is maybe something that will be taught in algebraic topology course. So yes, as I said, in the continuous setting, we need to watch out for singularities like jumps, discontinuity. Here's a corner, so this is continuous, but not differentiable. So differentiable essentially intuitively means the slope, right? And so here the slope goes up, here the slope goes down, but at this very point, there's no well-defined slope. Here's another example of a singularity. Here, there's a slope going down. Oh, here it's also going down, but here the slope is intuitively infinitely, negatively infinitely. So that can also happen. This function is not differentiable here at this point. And we will need to watch or have in the back of our mind such possible cases. So in the rest of this chapter, we will be dealing with partial functions. This simple means a partial function. It need not be defined on all real numbers. It could just be defined on maybe an interval, or partial functions on vectors need not be defined on all d-dimensional vectors, but maybe just vectors on the unit interval. And this is just some terminology and recap for your convenience from calculus, which of course you all have taken course of calculus, introduction to calculus. So let's now talk a little bit more and recall about derivative differentiation. Intuitively, that means the slope, and there's various way of denoting differentiation, the derivative. So some people call it g prime, the derivative of a function g. Some people write d by dy, the derivative of the function g of y, or some people write g prime, g point. That's particularly common when we talk about derivative with respect to time, t denoting the time. But basically, it's all the same, different terminology for the same thing, the derivative. And you all, I guess you even have learned about derivative in high school, right? So let's just briefly recall some rules about calculating the derivative. So for example, the derivative of a polynomial, x to the nth power, the derivative of that is n times x to the n minus 1, right? Remember that? Great rule, right? So for example, the derivative of the parabola x squared is 2 times x, right? But that also works for negative exponents. So for example, the derivative of 1 over x, that's just x to the minus 1. The derivative of 1 over x is therefore minus 1 divided by x squared, right? Let's recall some further rules for derivatives. For example, the derivative of the natural logarithm is 1 over t. The derivative of the exponential function is the exponential function itself. Derivative of the sine is cosine. Derivative of the cosine is minus sine. And there's the product rule. Derivative of f times g is derivative of f times g plus the derivative of f times g prime, right? You remember that? And then there's an important rule for derivative of a composition. So taking the derivative of the composition, f after g is f primes of g times g prime. Yeah, I'm sure you all learned that. So this is indeed just a recap. Right. So that's about differentiation in the one-dimensional case, right? So these rules are all differentiating a function of one real variable, this one here, right? So I'm going to put a 1 here to emphasize that. And now let's also recall derivatives of several variables of vector arguments. Here the terminology is, for example, if we have a function of 3 arguments, x, y, z, then if we want to take its derivative with respect to the second argument, we use this simple partial derivative with respect to y. Or sometimes if we don't want to use different letters for each coordinate, but just enumerate coordinates x1 to xd, then take, for example, the derivative with respect to the second argument. That's also common terminology. And again, this is different terminology for the same thing. This means derivative with respect to the second argument, and this also means derivative with respect to the second argument. And the rules are the same. So that already concludes our brief recap of differentiation, and now an even shorter recap of integration. Intuitively, integration means calculating the area under a curve, right? So here, like this. And the terminology for integral is this integral sign from a to b, right? So from a to b. The area under the curve f here, and dt means the variable with respect to which we're integrating. So that's integration. Technically, this is called Riemann integral. There are other types of integrals, and we need to sometimes be careful when there's a singularity, then maybe the integral may be infinite. This is a, by the way, oriented area. If we integrate from B to A in the opposite direction, then it's going to be the negative area. And the fundamental theorem of calculus says that this area can be calculated by finding the antiderivative of small f. So the opposite of taking the derivative, the antiderivative, that's basically integration, which is, if you think about it, this is very surprising, right? So the antiderivative is again a function. They mean the integral from a, any starting point, to x, and x now is the independent variable integrating over f. That's the antiderivative. And why is it called antiderivative? Because by the fundamental theorem of algebra, if we take the derivative of that with respect to x now, that recovers the original small f. And fundamental theorem of calculus thus connects the opposite of taking a derivative with the oriented area under a curve. And again, that's a one-dimensional case. There are also multi-dimensional integrals, area integrals, volume integrals. But fortunately, we don't need that. We do need one variant of this so-called Riemann integral, and that's a Stieltjes integral. Stieltjes integral, in the Riemann integral, we have this integrand, here it's called f of t, and we integrate it with respect to the variable t, right? dt means integration with respect to t running from a to b. And in the Stieltjes integral, integrand f of t is integrated not with respect to t, but with respect to another function, in this case, function g. So here we integrate with respect to g, dg of t. And the definition of this and properties are beyond the scope of this brief recap. So let me just report that in many simple cases, this can be expressed as an ordinary Riemann integral, namely the integral now with the integrand being f of t times g prime of t. So instead of integrating with respect to g in the Stieltjes integral, we can integrate with respect to t, as in the Riemann case, but now the integrand is scaled, is multiplied by the derivative of g prime. And yeah, just to be technically correct, there's a hypothesis, and that works when the function g is, of course, must be differentiable, otherwise this doesn't really make sense, but the derivative is supposed to be even continuous. It's called continuously differentiable. So yeah, later, actually, I'm recalling this for you because the Claude Shannon's theory of the differential analyzer shows that we need the Stieltjes integral, but it's nothing to be scared of. It's just basically your ordinary integral with an integrand multiplied by g prime. Okay, so that's our recap of differentiation and integration, all very simple. Now we need to move on to discuss differential equations, but first let's briefly recall ordinary equations and systems of ordinary equation with some examples. That's a good way, right? So here's a simple equation of one variable, x squared plus 4 times x plus 4 equals 0. And a question for you, what is the solution of this equation? This is not even high school, right? This is still middle school. Any guesses? Can you write your answer in the chat? You can either apply the formula, PQ formula, or you can just guess. So for example, yeah, -2 is a solution. Exactly, yes. You already write the solution here in the chat. Thank you very much. And this is a good example because whenever a mathematician sees any kind of equation, be it such a simple or very difficult integral equation, differential equation, mathematician will ask three questions. Automatically pops into the mind of every mathematician when seeing an equation. The first question is, does the equation have a solution? Right? And you've already answered that. -2 is a solution. The next question that automatically pops up is, in which mathematical space? So -2, in which space does it live? -2 does not live in the space of natural numbers, because natural numbers are only positive, right? But -2 lives in the space of integers. So this equation has a solution as in the space of integers. And so that's the second question. And the third question is whether the solution is unique, or are there any other solutions? So we've already found one solution, -2. Are there any other solutions? Question for you in the chat. Any other solutions? Okay, let's cut this short. Yes, there are no other solutions, right? So, I mean, technically, you know that -2 is a double solution, a double root of this equation. So in this case, we have no other solution. Let's apply these three questions to a little bit more complicated equation, namely the equation y squared -2 equals 0. Does this equation have a solution? What do you think? Yeah, these are simple questions, right? Yes, it has a solution, and the solution is the square root of 2, right? But this is already a subtle answer, because in which mathematical space does this solution live? The square root of 2 is not an integer. It's not a natural number. It's not an integer. It's not even a rational number. It's not even a fraction, right? That was this famous proof by early Greek mathematicians, like over 2,000 years ago. A Greek mathematician had to die. He was drowned for proving that the square root of 2 is not a rational number, because it was, at that time, it was an almost religious belief that every number is a rational number, every number is a fraction ratio of two natural numbers, but square root of 2 is not. So which space does this solution here live? It's the space of so-called algebraic numbers that includes all square roots or triple roots and so on. And the third question is whether the solution is unique. So square root of 2, unique solution, only solution to this equation B? No, it's not, right? Because minus the square root of 2 is also a solution, minus the square root of 2. So this equation has two solutions in the space of algebraic number. It has no solution in the space of rational numbers. So it's important to say which space we're looking for a solution in. And if we require that the solution is positive, then that rules out minus square root of 2, and then the solution becomes unique. And this is called a boundary condition or additional condition. Okay, let's now move on and consider another equation, y squared plus 1 equals 0. Does this equation have a solution? Well, it does not have a solution over the real numbers, but it has a solution over the complex numbers. That's why complex numbers have been introduced, right? And the solution of this is I, right? So the complex unit number I. And so this equation has no solution over integers, no solution over rational numbers, no solution over real numbers, but over complex numbers, this space of complex numbers, it has a solution I, and it actually has two solutions. It also has the solution minus I. So the solution is not unique, and we cannot even make it unique. We cannot impose such a condition like this here. This is fundamentally impossible. You may learn about this in complex function theory. So these are three examples about the three questions that every mathematician asks when seeing any kind of equation. Now let's move on to systems of equation. So here you see a system, three equations, each equation in three variables x, y, z. And what does a mathematician ask? Does this equation have a solution? In which space does it live? And is it so unique? And so for those of you who know about linear algebra, the answer is yes, this system of equations has a solution in three-dimensional Euclidean space. And this solution is also unique because this system of equation actually comes from a so-called Vandermonde matrix. And Vandermonde matrices are invertible. So if you have learned about linear algebra, then these questions are easy to answer. Well, that's the whole point of linear algebra, to answer these questions for any given type of such systems of linear equations. And The geometric picture may be also helpful. So each equation, each single equation kind of defines a plane, affine plane in three-dimensional space, right? Three-dimension x, y, z. And so here's a picture of three planes. Maybe this corresponds to the red plane. The second equation corresponds to the yellow plane. And the third equation corresponds to the green plane. And a system of equations means all three equations must be satisfied simultaneously, which geometrically corresponds to the intersection of these three planes. And that's this point. And this point is therefore the solution of this system of equation. And you see that this is a single point, therefore it's a unique solution. If the planes are arranged in a different way, then there might be no solution. For example, if two planes are parallel, or there might be infinitely many solutions. But anyway, so that all these things can happen when we talk about equations and systems of equation, and the question that every mathematician asks when seeing such an equation. Now let's move on from equations about single real numbers or vectors of numbers, right, tuples, to equations about functions. Here you see an example of an equation for a function. This equation asks for a function e, and it's called a functional equation. Namely, the solution function e must satisfy that e of t plus s must be e of t times e of s for all t and all s. So now t and s are real numbers, and e is a function, and we're looking for a function that satisfies this equation. And so again, my question for you is, do you know a solution? Does this function equation have a solution, and the solution is now a function? Can you imagine a function that satisfies this equation, that turns addition in the argument to product multiplication of the values? Yes, exactly. The exponential function has this property, right? Exponential of t plus s is exponential of t times exponential of s. So it has a solution. We postpone question number 2 and proceed to question number 3. Is this solution unique? Is the exponential function the only solution to this functional equation? Or can you imagine another function that also has this property? Not just the exponential function, but yeah, for example, 2 to the x, 2 to the t plus s is also 2 to the t times 2 to the s, or 3 to the t plus s, or 4. So not just the exponential function e to the x, but any exponential function q to the s has this property. So this solution is not at all unique. There are many solutions to this functional equation. Anyway, yeah, let's now move on to differential equations, which is a special kind of such function equations. And again, I'm going to start with a example, namely the differential equation f prime equals f. Okay. So f prime equal f. Again, question 1 for a mathematician: does this equation have a solution? Well, yes, it has. Solution is, again, the exponential function, right? Exponential function, recall, has this property. If we take its derivative, then we recover the original function. Next question, is the solution unique? Third question, actually. Well, 3 times the exponential function also has this property. 7 times the exponential function also has this property. What did we last time when we had several solutions to an equation? We would add an additional condition. But right. So here's the condition. We add the condition f of 0 equal 1. What you see here is a geometric way of imagining solution to this equation. So this, what you see here is the vector field. Vector field takes 2 real numbers, 2-dimensional vector field, t and y, and returns 2 real numbers, in this case 1 and y. And then imagine this to be an arrow, right? So the larger that y gets here, the larger that y gets here in this direction, the longer the arrow, right? So in direct x direction, it's always length 1, but in y direction, it becomes longer and longer. And the solution to this equation is basically intuitively following these arrows. So here the arrows go more in this direction, but here the arrows become more and more in y direction, and following these arrows, that's the solution to this so-called differential equation, because it has a derivative here to the left. And then question whether the solution is unique is answered yes. So the exponential function is the only solution, which geometrically makes sense, because if you just keep following the arrows, there's no way of deviating, right? At each point, an arrow indicates where you should now move, in which direction you should move next. Okay. Good. So now let's look at more differential equation. So here's another differential equation, g prime equal t to the k, where k is a constant. Let's say k is equal to 1. Okay. So here you see also the terminology g prime or g point. And let's say k is 1. So the differential equation says g prime of t should be t. Does this equation have a solution? Let's jointly find a solution to this equation. Yes, t squared over 2 is a solution, right? Because if you remember the laws of differentiation, t squared over 2, the derivative of that is t. So when k is equal to 1, we've just found a solution to this equation. So, and this is a continuously differentiable equation. It has no corners in the graph. And we're going to again add conditions to make the solution unique. We want only positive arguments t, and we want the value of the solution to be 1 at argument 1. So that's one kind of a solution. And when we can try to solve that, we just solve that when k is equal to 1. We can try to solve that also when k is equal to 0. When k is equal to 0, this means 1, right? So then we have another differential equation. G prime must be equal to 1. What's the solution for that? Well, the solution for that is t. Of course, if we take the derivative of t, then the derivative is 1 exactly as required. And t of 1 is equal to 1. We can try to solve this also for negative k. So for example, when k is equal to -1, then ask for the solution g prime of t equal to t minus 1, t to the -1, that's just 1 over t. What's the solution? The natural logarithm. Remember that from the last slide? So for each k, we can thus find a solution to this differential equation. And with this condition, it also becomes a unique solution. Now moving on, more complicated differential equation. H prime of t should be equal to y prime, where y is any, let's say, continuous function. So this is a special case. Item G is a special case of item H. In item G, the function on the right-hand side, y of t, was a polynomial, t to the k. Actually, many different polynomials. And this is a more general case when y is just an arbitrary fixed function. Can we solve that differential equation? Well, yes, this is where the fundamental theorem of calculus comes in, right? Fundamental theorem of calculus says, take the antiderivative of y. Take the antiderivative, the integral, then its derivative recovers the original function of y. So, and again, with boundary condition, this is going to be the unique solution using the fundamental theorem of calculus. Let's now make things a little even more complicated, stepping up a notch. Now we're going to look at the so-called second order differential equation. So here, the left-hand side was always first derivative, f prime, g prime, h prime. And the next one is a second order, u double prime. Second derivative should be equal to minus u. Okay, question for you. Can you solve this second order partial derivative? Remember what we learned about the rules of differentiation? What is, for example, the derivative of sine? The derivative of sine is cosine, first derivative. The derivative of cosine is minus sine. So that sine is the solution to this equation, right? Is it unique? Well, let's try cosine to start with. The derivative, first derivative of cosine is minus sine. The derivative of minus sine is minus cosine. So cosine also solved this second order equation. So it's not a unique solution. And we make it unique by imposing two conditions. One for the so-called initial value, u of 0, and one for the derivative at the initial value, because this is a second order, we're going to need two conditions. So now we've already solved the second order differential equation. Next, we're going to look at a system of differential equations. So here we have a system for two functions. We want to find a solution which consists of a vector, a tuple of functions. So this is combined. U prime should be v, and v prime should be minus u. Can we solve that? Can we find a solution? Well, yes. U, let's try u equal to be the sine, and v equal to be the cosine. Then taking the derivative of sine is equal to cosine. Taking the derivative of cosine is equal to minus sine. So that's a solution. But also, starting with cosine and here minus sine is also a solution. And you can see that this is basically the same as this single differential equation. We have reformulated this single second order differential equation as a system of two first order differential equations. And that's a general technique that one can do always convert a higher order differential equation into a system of first order differential equation with initial conditions. Now let's move on and even further consider this differential equation W, first order W prime, should be equal to the square root of W. So what's new here? New here is that this is a nonlinear differential equation. Previously, the right-hand side was just the function itself, or a constant function, right? This was y, independent of h. This is linear. This is a system of linear. But here suddenly we have a nonlinearity, a square root. And that's where things start to get messy, because even if we impose such a condition, initial condition, then this single differential equation suddenly starts to have infinitely many solutions. So here you see infinitely many solutions, and I want to challenge you and ask you to calculate, verify that for every capital C that is positive, this function is a solution to this differential equation. So don't ask me how I found this, but simply verify. Do the math, calculate the derivative, and verify that the derivative coincides with the square root of it. So this third question of mathematicians, not only is the solution exist, but is it unique, actually starts to become very subtle when we talk about differential equations. But this is not to scare you too much. Let's just keep it in the back of our heads for a moment. Okay, so differential equations. Now we've seen many examples of differential equations, and now we want to classify them. And that's probably going to be all we, no, we have still time for, fortunately, yes. So this is going to be classified. That's a pun, right? Classified can mean secret, but here it means we're going to distinguish different classes of differential equation. So the first differential equation that we saw here is a first order differential equation. It only involves f's first derivative. It is linear, no square root, no square, linear, and it's homogeneous. It does not contain any term that depends on t only. Whereas the second differential equation here for g, that's also first order. It's also linear, but it's inhomogeneous because here there's something that depends on t, inhomogeneous. First order, linear, inhomogeneous. Okay. Then the next equation, remember, next one involves second order derivative. So this is a second order differential equation. It is still linear, and it's again homogeneous, nothing that depends only on t. Next one we discussed is again first order, but it's now a system. Two equations for two functions to be found. The last example that we discussed is first order, but it's nonlinear, and it's homogeneous, nothing that depends only on t. So, we've already seen many different types of differential equations. I don't expect you to be able to solve them, but I do want to encourage you to verify that the solutions that I have thrown at your face, that these are actually solutions, right? And particularly the infinitely many solutions to this one. Now let's consider another system of differential equation, namely here system with non-constant coefficient, right? So here the coefficient is implicitly 1. Here, everywhere coefficients are 1, -1, -1. Here's also coefficient 1, but here's a constant 2 times t, right? And this is non-constant coefficient because of course t is variable, right? So this is an example of a first order linear differential equation, but one with non-constant coefficients. And here's another example of a very simple differential equation, y prime equal 2. That's a special case of this differential equation g here, right? When k is equal to 0, then it's just a constant. And the solution of this one is, solution of this equation is y of t equals 2 times t. And you see, this is actually what's written here. So this is just a different way of reformulating this non-linear differential equation with non-constant coefficient as a system of two equations with constant coefficients, right? And we're replacing 2 times t here as a non-constant coefficient with a solution to this differential equation. Y does not change anything, but now all constants are we have only constant coefficients. So that's another important technique, rewriting a differential equation with non-constant coefficient as a system of differential equations with constant coefficients. And then this latter type of differential equations are called autonomous. They are autonomous because they're independent of time. When the coefficients don't depend on time, if we start the differential equation a little bit later, it will evolve in the very same way as if we started earlier. It's independent of time, and that's called autonomous. Time-independent system is also synonymous to being autonomous. And finally, we want to see an example of a so-called implicit differential equation. So here you see z prime, so first order derivative, but it's squared. So this is nonlinear. So it doesn't say like here, x or w prime should be equal to something, h prime should be equal to something, but some equation involving z prime squared minus wt should be equal to 0. So that's a first order nonlinear implicit differential equation. Okay, so that was a lot in a very short time, and I can understand why if it was too much in short time. So that's why I'm recording all this and providing you with the slides so that you can review it later. Again, this is just a very condensed summary of the many things that you learn in a course on differential equations. So again, opportunity for me for some shameless cross-promotion. Please consider taking a course on differential equations from the math department. You won't need it to pass this course, but it will certainly not hurt. And by the way, we're only going to need this in this third chapter on analog computing. So if you feel kind of lost, don't worry, just keep watching, and we're going to move on to applications of these differential equations. Yes, because now we want to start learning about Vannevar Bush and his differential analyzer, which is an ingenious piece of mechanical engineering. So let me show you a short video about the life of Vannevar Bush. And one thing I want to point out is how long does it take to get a PhD? So when Vannevar Bush joined Massachusetts Institute of Technology, he announced, he yeah, he said he was going to earn his PhD within 1 year. PhD in 1 year. Do you know anyone who got a PhD within 1 year? Well, not Vannevar Bush, because actually he beat his own promise. It took him only 9 months to get a PhD. So here's the video.